project, terahertz communication systems, which I feel more aptly named optical communication systems. So before we begin, this is just brief what we're going to be talking about. First, I'll talk a little bit about the background theory, a little bit about communication, a little bit about optical communication. Then we're going to talk a little bit about the current state of the art of optical communications. We're going to focus mainly on ground and space-based communication, or space-to-ground communication. The why do we want to use optical band for communication? Current solutions, what people are doing now, what ESA, what NASA, what JAXA are all doing. My solution to the problems that optical communication band, or optical communications itself experiences. My solution, some design, and then we'll walk over to Tinker, and I can show you my hardware setup, and we can have a Q&A of that. So, to begin, a lot of communications, well, most communications, if not all communications, done using the electromagnetic spectrum, and I'm sure you've all seen this graph about radio waves on the left, gamma waves on the right. And most of our communications, whether it be Wi-Fi, whether it be communicating from continent to continent, from ground to space, usually ends up being the radio waves and microwave band. And there's just clear reasons to use in that band, and we haven't really divulged up further into the infrared and beyond. So optical communications is sort of the next step, moving away from the microwave band for communications up into physical spectrum. So again, a little bit of theory about communications. Right? This is the map that all RF engineers, or communications engineers, deal with. Essentially a roadmap of how the electromagnetic energy travels from the transmitter side to the receiver side. So on the left-hand side, you have transmit power level. So it's a set power level, a set dB, and as it goes from left to right, it travels along these different paths and losses. So you can sort of assume that, well, you can sort of see that the x-axis or y-axis going up and down is sort of energy of your signal, and this is what happens along the way. So the greatest loss in optical communications is the path loss. And we'll talk a little bit more about that later, but just because the frequency is so high, your free space path loss is a lot higher than, say, the UHF band or the VHF band. And specifically what my project is going to be focusing on is the receiving side, the antenna gain side. So your antenna sort of is a directional focusing of the electromagnetic energy. So then you can have a very highly directional antenna that helps increase the energy level. And what's really important is the energy at the receiver end and the energy of the sensitivity of the receiver. So that gap is your link margin. And for a lot of space communication systems, they attempt to get a link margin between 6 to 10 dB. There's a lot of factors that go into play into trying to get this 10 dB link margin. You can increase your transmit power, you can increase your receiver gain by choosing a different antenna, different directionality. There's a lot of little facets, just in like a lot of things in engineering. You can do a lot of things to get that margin. And one of the things that you can do to get that margin is increase your receiver gain. So NASA has the deep space network. They have giant, large antennas, 20 meters in diameter, to communicate from everything from the Mars rovers, Mars satellites, to Dawn spacecraft, all the way to Voyager, which is at the edges of our solar system. So this is a fantastic slide that JPL put together. It really represents sort of different applications and what data rate do you really need it for it to become feasible. And this red line sort of shows where our technological cutoff is with the current technology using microwave band to transmit all the data. And if you really want a high density science data or high quality video data coming, say, live streaming from Mars, excluding the time delay, then you really need an order of magnitude improvement in the data rates that you currently can't achieve. And this is the reason why a lot of agencies like NASA and ESA and JAXA are focusing on the optical communication path, because they want to be able to improve their downlink markers. To give you a perspective of what NASA, the Maven mission uses, it's a satellite currently orbiting Mars. Its most recent discovery was how Mars lost its atmosphere. It also does a lot of telecommunication relays for the rovers. It also does very high quality mapping of the surface of Mars. But its downlink band, or downlink rate for the X band is only 550 kilobits per second. 550 kilobits, to put that into perspective, the average global internet speed is 7.6 megabits per second, and we think that's slow. So engineers and scientists would love to have this bottleneck not exist in the optical communication band, or using optical communications is why do we want to use optical communications? So these are 4 advantages to it, and there's always cons to why optical communication is not great for spacecraft. So the advantages, there's essentially 3 things that are limited on your spacecraft. There's power limitations, there's volume limitations, and there's mass limitations. Take Voyager again, for example. Its entire spacecraft revolves around a giant antenna that has a volume impact to it, it has a huge mass impact to it, and it requires a relatively powerful transmitter to be able to communicate. And the data rate for Voyager right now is something ridiculous. It's 10 bits per second. Very small because you can pack it. It's all about energy per packet and stuff like that. But optical communications allows you to have a smaller footprint. So now you can use those resources that were previously allocated to the communication subsystem to doing more science, to doing a bigger structure, to doing something else, or to have a cheaper launch because it's smaller, less weight. It's sort of, if you can improve this technology, it has benefits in other subsystems. And then another, the obvious improvement is you have greater bandwidth, higher data rate with optical communications. So you're not limited, say, in X-band, maybe it's limited to 5 kilobits per second. You can really go forward. And we use, optical communications if you think of fiber optics. Fiber optics on the ground, we really use infrared band or visible band for our communications under the Atlantic. And we had fantastic data with gigabits per second. But again, we're talking about free space optical communications, so a little different than fiber optics. And then another great benefit is less interference. So right now, the CubeSat sort of idea is really exploding out there. A lot of universities, a lot of private industries really want to get CubeSat out there. And in order to get a CubeSat out there, you have to go through licensing with the FCC and the ITU to have your allocation in the frequency spectrum. And that it's actually a really long process. It's like a 6-month process to get a license to get into space. And if your satellite that you're building takes only 4 months, then it's a real bottleneck. And by having because the beam width of an optical communication system is so much smaller, you can have less interference between different satellites. And now this beam width idea comes into one of the cons of optical communications, and that is in the pointing requirements. So it imposes a new restriction on another subsystem of your satellite, in that in order to be able to communicate, now you have to be able to precisely know your orientation in space and precisely point your spacecraft in the right direction. But these are definitely surmountable obstacles. It's not the end all. But the next big problem with optical communication systems is the large free space losses. So free space loss is proportional to the square frequency. So if you go to terahertz and the optical, your downfall is that your free space loss is not double bigger, but 4 times bigger than whatever you were using in the microwave band. But the benefit again, the cons and the benefits play off each other in that because you have such small beam width, you can get very large antenna gains. So it's what is the medium ground, or the ideal situation is where you have a receiver that you can make big enough, and that you can make that link motion work. So current solutions to the problem, so what NASA, what ESA, and what some private industries are starting, or private companies are starting to do, is use commercial off-the-shelf telescopes. These are your basic telescopes, like 16-inch, 20-inch. This particular telescope is JPL's Octal. It's an optical communications terminal link, or lab. Essentially, it's been used to communicate with one of the satellites around the moon, and been used to communicate with the ISS. So this is a standard 16-inch or 20-inch glass mirror telescope. And this is they're essentially using the technology that exists. Let's just use a telescope. But the problem with, say you want to communicate much further than that, you're going to need a receiver that's bigger. And building bigger glass telescopes does not scale linearly. It does not scale quite to the square. It scales much more. If you make bigger telescopes, it's a lot more expensive. It's a lot harder to do. So, if you want a great optical communication link, and you want to communicate to Mars, say, then you're going to need a bigger telescope. And the downside of that is going to cost a lot more. So, the solution to that is to use a Mylar vacuum-based parabolic telescope. So, the initial problem is that it costs $1 million, $10 million, $100 million to build giant telescopes. For this base telescope, it costs you $50 to make a 21-inch telescope. And so that comparison just shows what using this method goes beyond using this glass case. And the reason why these telescopes sort of cost so much is because they're creating an image. You don't need to create an image when you're doing communications. All you need to do is act like a photon bucket. So all you need is as big of a collection area as focusing, sort of like a focusing angle, so you can get all the energy you're trying to collect to your response. So by reducing the requirements of having this optically gray telescope, you can now have just this cheap Mylar system. And the Mylar system works, and we'll go to the lab and you can check it out. This is just uniform deformation of Mylar. Mylar is just a plastically aluminized siding. One side's aluminized, so it's reflective. And by uniformly deforming that, you sort of create a very close to a parabolic shape that you want to actually focus light down to. And by placing your receiver, your transmitter on the focus point, you can now receive the transmitter. So before we head into the lab, I just want to show some of the things that I can't really show, just some CAD drawings and data that I've done. So this is just a CAD drawing of a transimpedance amplifier for my photodiode on the receiver side. So the photodiode essentially is a sensor that converts light intensity to current. In order to have a microcontroller to read that, microcontroller read the voltages, so it's a transimpedance amplifier that converts the current to the voltage with X amount of gain, and it's proportional. And you can just set it up. This was a PCB that I designed, PCB that I sent out, I built, and it's in the lab, and I can show you how it sits inside one of the telescopes right now. So that's just an EagleCAD, that's just a little CAD drawing of the schematic and the PCB board itself. And this is an example of like one of the packets I sent. So this is a setup of microcontrollers hooked up to the receiver that I just showed you. And it's just sampling as fast as it can, trying to get the dips from the light source. So I had the light source on one end of my table, the photodiode on the other end of the table, and as I modulated the LED, I can now see the modulated output from my transimpedance amplifier. So this here, I'm sending two characters, I believe. It's A and 0, just ASCII text characters. And you could bit bang out the binary and look it up in the table and figure what it is. But as a quick preliminary test, I wanted to see if my transimpedance amplifier was working, and this was just validating that my current to voltage is equal. So with that, I will take any questions about the slides, and if there are no questions, you can just go to Tinker, and I can talk a little bit more about the hardware by standing in front of it, and you can ask me more questions then.
So I'm not a communications guy myself, so I'll have the basic one on that. So since light is so much better, why is it that it hasn't been used? Why hasn't it been used before? I mean, is it just the fundamental reception problem? We had to overcome those on the others as well, right?
So yeah, so as I understand, why did Marconi use the radio frequency spectrum, not light-based communications? And as I understand it, I believe it's because to get photons to emit from a wire from the radio waves is lesser energy. So it's easier to radiate from a wire than it is to radiate from a light source. Okay. At least that's how I understand it. I might be wrong with that. But why light isn't used right now? I think because we haven't had the technology like continuous powered lasers, or it's a really high risk factor because the pointing requirements are so tight. Mm-hmm. And with if you're communicating with the X-band, right, from Mars to Earth, all you have to do is roughly point in the right direction, and then your beam spread is going to be big enough to encompass Earth plus a lot. Mm-hmm. So with the optical band, you definitely have, we're talking about micro-radiant pointing. So that's just a challenge. Why it's not been used in space before. But I guess to follow up on that, it has been used in space, and the idea of lasercom has existed for a while now. And I believe it was early 2000s or late 2010. NASA sent the LCD mission, which was the satellite that now orbits the moon, and had an optical terminal that communicated with the JPL terminal. And they had a data rate throughput of 622 megabits per second. So it's sort of a lot of the technology, when it comes to space where it's really high risk, they really like flight heritage on it. And they don't try to make big leaps because it's just a risk factor they don't want to take. But ESA recently did a satellite-to-satellite intercom communication system. JAXA is trying to do it, and there are some small academic institutions that want to do CubeSat-based optical to ground communication system. So the technology is definitely growing there. And so sort of my project focuses on is the receiver side, how you can make that cheaper so that it's not as expensive. Yeah.
How does it compare against the mirror?
So the mirror, right, is like diffraction limited to it. And I guess when you mean comparison, do you mean like optical quality?
Well, you've got this expensive mirror that you're replacing.
Right.
Can you match the performance, or can you
Well,
make a bigger mirror that you could do otherwise?
let's see.
Head-to-head comparison of how it performs from a communication standpoint.
I did not do a head-to-head comparison, but sort of I've been thinking of it this way. If you want, your communication system sort of just a photon bundle. Right? You're trying to collect as many photons as possible, and you're trying to send it to pin dial, in the, I guess, best manner. Like, you just want the biggest area possible. So a really cheap way to do the biggest area possible is not via glass-based mirror systems, just because the bigger, the more expensive it is. So the sort of, I guess, the thing is that you don't need the optical quality of the glass.
Right. Well, so my question is, can you catch more photons?
So there is an efficiency loss because it's not as optically sound. The thing is that efficiency loss could be offset by making it bigger. So it's not going to be like a 16-inch glass telescope is not going to be the same as a 16-inch Mylar telescope, but I bet a 16-inch glass telescope and then say a 30-inch Mylar telescope. The 30-inch Mylar telescope is still going to cost pennies on the dollar. And I haven't tested if we did enough, but I believe it would be.
So that's a direct, can I just follow on that for 1 second? That was my question is, if it's $50 instead of $10 million, why don't you make a 1 mile, no Mylar?
So the problem with that is, again, pointing. You need to be able to point these things relatively, the vector pointing between transmitter and receiver has to be within some offset. If you made it 1 mile long, then you can't move it unless you put it in space. So.
But you could make a really big one that you could move.
You could.
Really cheaply.
Yeah, you could make like a 20, 30, 40 meter one. And the great thing about, the bad thing with glass is that it's really heavy once you get to really big sizes. And the structures required for it might cost as much, if not more, than the mirror itself. And with this Mylar, it's really lightweight, so you can make a large structure that's still easy to build.
My other question is it possible to transmit potatoes?
Transmit.
Meat potato.
Took me a minute.
So just a quick comment first and then question. So regarding Marconi, I think it was, initially it started out with Spark, this is what he was creating. And that Spark frequency, going back and forth, I think is what dictated the radio frequency thing that he used.
Okay.
And I went pretty far.
Yeah.
So,
I mean, the free space loss at like 144 megahertz is a lot less than a 445 megahertz. Just how the math is done.
my question, so the Mylar, is it photon frequency sensitive?
So there is, the reflection of, so it's aluminum based, so it's the reflectivity of aluminum at different wavelengths. And it peaks at a certain wavelength, right? So gold is the best for, say, infrared. Aluminum and silver, different.
What's the range for each of those, right?
Yes, there's plots that tells you, okay, to peak in this, so what you want to do is sort of, if you know the frequency that you're going to be using, then you want to, sort of just like how you're going to tune an antenna, you're going to want to tune your telescope so that it reflects the most of that.
When you're getting information from afar, would you like to have it a narrow frequency domain, or do you, is it as broad okay?
Right, it depends on, like frequency modulation versus amplitude modulation. And in the case of optical communications, you can't really do frequency modulation just because it's sort of like a solid state, steady state item. So what you do instead is just amplitude modulation. So it's okay if it's a narrow range. And actually you want it to be a narrow range because if it was a wide range, then you have a background.
Right.
So
that's what I was.
yeah. So if you had a narrow range, maybe even in a lot of the other designs that are a little more sophisticated than mine, say glass grids, they use a lot of bandpass filters just to filter out all the other stuff so that they can just get the lowest noise floor, again, receiver sensitivity as low as possible so that their signal strength is much higher.
So have you done any calculations on the size you believe would be required to have something like this?
I did actually.
Receiving
So there's this competition called NASA Centennial Competition. It's a CubeCast competition. It's the biggest sort of like government cash prize award out there. And essentially it's a CubeSat system that's supposed to orbit around the moon. And I wanted to just figure out, okay, if I had a 10-centimeter aperture on my little 6-foot cube satellite around the moon, how big of a telescope do I need on the ground to be able to see? And it really plays off on what is the transmit power and what is the distances, what is the frequency I'm using. And I calculated that I could use say a 20-inch telescope and be able to communicate straight to the moon. But you might as well make it bigger because why not? But yeah, I have an Excel sheet that goes through essentially, it goes through this and it just calculates the dB losses and then adds them up and tells me what my margin is. Now, one thing that this doesn't really go into is sort of like errors and like like the energy per bit, sort of figuring out what you need for 10 to the negative 6 bits, how many energy do you get? Sort of, it doesn't really deal with this. This map really won't figure it out, and I sort of just focused on this.
Unrelated to the project, what are your post-graduation plans?
So I am actually going to be a researcher. So I am the system engineer at Andesite, which is the EU's Cube Satellite project. And Brian Walsh, who's a new mechanical engineering professor, he recently got a grant from NASA to build a new Cube satellite called Cubic. And it's going to be an X-ray telescope with satellites. So he hired me at least for a year, if not longer, to work on that project. So it's a collaboration between Goddard, BU, and I want to say Princeton as well, Physics Center.
In the interest of time, let's go see your demo.
Yeah, yeah.